share my screen. Okay, can you all see my screen?
Yes, sir.
Yes, sir.
Okay, so we were talking about time frequency analysis. We talked about temporal overlapping and zero padding in the previous class. There's this one question about shape of the window, whether the type of window that you use affects the time frequency resolution. That question wasn't answered, and that's what I'm going to do today. Okay, and that will lead us in a very natural way to talk about Hilbert transform, which is the uh, topic of interest today. Okay, so just a quick recap. This is time frequency analysis. Different types of windows determine your time or frequency resolution. A multi-taper method sacrifices frequency resolution in order to put more than one basis function inside the tile, and it's a trade-off that you can do. And then we also talked about wavelet transform very briefly, in which a single function called a wavelet is squished or stretched to generate multiple to generate your entire set of basis functions, and then the signal is just projected on these basis functions. Okay, so projection means taking an inner product. So when I say I project the signal on a basis function, means I'm taking an inner product. It's the same thing as doing this thing. So essentially, you've got a filter bank or a set of basis functions sitting inside each tile, and you take an inner product with each of those basis functions to generate a representation that looks like this. Okay, and this is the wavelet transform, where you can see the transient as well as oscillation both um, in the time frequency spectrum. So you can see this as well as that. And with a short window, you can either see this, with a long window, you see that, but not both. Okay, so now let's get to this question that how does the shape of the window determine the frequency resolution? Now, what I've been telling you is that when you have a window of length n, or well, let me put it in units. So if a window has a length of time t seconds, so that you're computing the FFT over uh, a length of time t, then the frequency resolution is 1 by t, right? That's what we have talked about, irrespective of the window size that we use, right? So the frequency resolution is 1 by t. That's where you get a frequency point in Fourier transform. So suppose you've got a second signal of length 2 seconds, then your frequency resolution is going to be 0.5 hertz. If it's a 500 millisecond window, then it's going to be 2 hertz and so on, right? So that's what we have talked about. However, we can actually, by the way, this 1 by t is called the Rayleigh frequency. That's where you get an estimate of the amplitude and the phase of the signal in the frequency domain. Okay, so you compute the Fourier transform at those frequencies. But you can ask a more nuanced question, which is that if I've got a signal like this window here, for example, then its energy is spread in both time and in frequency. And I can actually talk about this distribution of energy in time and frequency and think about the resolution in terms of those. So let me make this more explicit, and this actually leads us to the precise definition of the time frequency uncertainty principle. So here's how we define it um, formally. So if I've got a signal ST, okay, whose total energy is E, given by this formula. Remember, this is how we define it. The energy of the so you take the signal, square it, and integrate it over time, you get the total energy. And what Parseval's theorem tells us is that this is also the signal in the frequency domain. You take the square and integrate over frequency. Okay, so now think about this. Um, this st square, the mod, or s omega mod square, as the energy density function. Okay. So, in fact, you have to normalize with E. So, without loss of generality, you can just think that E is 1. If not, you just divide this by E so that this whole thing becomes integrates to 1. So, this is like a density function. This is like a probability PDF, probability density function, which we had discussed way long back in our first module. So this tells you how, where energy is concentrated in time. This tells you how the energy is concentrated in frequency. Okay. So without loss of generality, we mean E is 1. So now I can talk about things like what is the average time of a signal, which is just T multiplied by this energy function. This thing will get maximized wherever the signal has maximum energy in time. So for example, in this sort of a basis function, the average time will be right here in the center. That's where the energy is maximal. Assuming that it's symmetric. If it's not symmetric, you have to just integrate it in this way. So this is telling you where the energy density is, where the energy of the signal is in the time domain as a function of time, and you multiply it with time and integrate it. This is like the first moment, okay, the mean signal. Likewise, I can also define how the energy is spread out around this mean. This is like the computation of variance. So I say t square is the square of the standard deviation of time, and this is how you would compute it. This is exactly the way you compute the mean and variance of any random variable, right? So this is just nothing but, think of this st square as fx um, t, where that's the probability distribution function, probability density function, and this gives you a standard deviation in time given by this formula. Now this thing is going to vary depending on the type of basis function that you have, shape of the signal, correct? Because it's based on how the energy is distributed in time, which is going to depend on the shape of the signal and so on. Likewise, I can define an average frequency of a signal like this. This is just thinking of this particular function, s omega mod square, as the energy density function. So this is where the average frequency is. And I can also again define the standard deviation, which is the variation in frequency over variation in frequency about the mean frequency. So suppose I have got a Gaussian function, just to give an example. Um, so if I, sorry, pen function. So if I got a function in the time domain which is a Gaussian function. Okay, in the time frequency domain, this is going to have an sort of, it's going to be a 2D Gaussian in energy. Okay, so the marginal here is going to be a Gaussian, here also it's going to be a Gaussian. The more stretched out it's in time, the more squished it gets in frequency. So these are the density functions. This is your ST square and this is S omega 1 square. Okay. And then your mean time and mean frequency are both well, the mean time is going to be this time here and the mean frequency is going to be this, and the standard deviations here are your t square and, oh, sorry, the variance. Okay, any questions on this? This is fine, right? I'm just defining this as energy density function. In Parseval's theorem, it says that you can either integrate over time or over frequency to get the energy. This is fine, right? Any questions? Okay. So now let me tell you what the actual time frequency uncertainty principle is. And this proof is there in this book, Cohen, Leon Cohen's book, Time Frequency Analysis. It's an excellent book. It's also relatively easy to read. So if you are interested, this is a good book for you to follow these concepts on. So the time frequency uncertainty principle is this: the product of time, standard deviation in time and standard deviation in frequency is always greater than or equal to half. It can't be less than half. Again, if you are thinking of this from a tile point of view, T and B, the area is half. Okay, but note that this is not the actual tile that we had talked about in previous classes, where this was T and this was 1 by T. This is actually the density, how the energy is spread inside the tile. And it's a standard deviation in time and frequency domain. So it actually means slightly different. Now turns out your different tiles or different windows uh, actually have different concentrations of the energy in time and frequency domain. So this product multiplied by V is half only for a Gaussian signal. There's no other signal for which T multiplied by B defined this way is half. So in other words, this Gaussian window is the most compact window that you can get. Or the Gaussian tiles in your time frequency space here are the smallest. In terms of the spread of their energy in about their mean and mean time and mean frequency, the spread of the energy is least for a Gaussian. So then why don't we always use a Gaussian? Remember, I had earlier talked about Slapian windows being most concentrated. So the idea here is that the reason why a bunch of other windows are also used while doing like panning and so on, because those windows have could have better properties than a Gaussian in terms of phase properties as well as how energy is concentrated within what you define a tile. Okay, so think about this. It's a, when I say it's a Gaussian like this, right? And then this is the standard deviation. And then this much energy is sort of leaking out, right? This, so in the time frequency domain, you can think of at any tile, you've got some energy which is concentrated and some of it is leaking out. This is spectral leakage. Now, what this statement tells you is that this size is smallest for a Gaussian. The product of a time and um, frequency standard deviations is smallest for a Gaussian. However, it doesn't mean that the leakage that you are seeing here is minimal for a Gaussian. It just means that the tile. Now you can actually say that, hey, is it possible for me to have a slightly bigger tile? So the tile is slightly bigger, but more energy is concentrated inside the tile. That is what a Slapian window. Okay, so it has a slightly bigger tile, but the energy is more compactly concentrated within the tile. In fact, if you had a set of functions, you say I'm going to have a set of functions which are all orthogonal to each other, and I need maximal spectral concentration within the tile, the Slapian window is going to do it. But it will be a slightly larger tile than a Gaussian tile. Okay, so this is the answer to this first question, that time frequency resolution, it does matter on the shape of the window. It's maximized for a Gaussian. Gaussian tiles are the best, but it just means that they are the smallest, and uh, better properties. Like for example, the size could be slightly larger, but a higher proportion of the energy might be concentrated, which is what you have with Slapian tapers. And when you get to phase, for example, where, for example, you want to have a linear phase, um, or some other properties that I'm not talking about here, you might want to choose a different window, like a Hamming window, Hanning window, Blackman window, and so on. Filter design is a course in itself, so I'm not getting into too much detail here. And just saying that different windows will have different properties on how they represent the signal, and you choose a window depending on uh, you know how you want to represent yours. Okay, so that's that. So we are finishing our time frequency and analysis now, from a filter bank point of view, and I'm going to now talk about a different way of thinking about it next. So if there are any questions about this, please let me know. Otherwise, I will move on. Okay, so let me move on then. Talk about a very
Yes.
important concept, a Hilbert transform.
Sir,
Yeah.
just uh, the previous slide. So that means that the Gaussian tile should have at least a minimum area of 1/2.
Yeah, it depends on what you mean by area now. If the area is defined like this, T multiplied by B,
Yeah,
where this is the standard deviation and this. So for a Gaussian, it is half. Yes.
it should
But
be
when I
exactly
draw
half.
the tile here, in these kind of plots, when I draw a tile, I'm essentially asking where I am putting the window in time domain and where am I getting the frequency values, right? So if any window has a length of t, duration is t, this is the length of the window, not the concentration in time. Then the frequency points are obtained at 1 by t, or multiples of 1 by t,
Yeah.
irrespective of what you are doing. So this 1 by t is then called the Rayleigh frequency. That's where you are getting an estimate of this. It doesn't of the frequency, of the Fourier transform. It doesn't tell you anything about the constant which is defined in this way. This is the the standard deviation, the concentration of energy around the mean. If you define it, then equality is reached only for a Gaussian. It is equal to half. Yes. Okay.
Okay.
All right. So now we are moving on to the Hilbert transform. And the reason I talked about this interpretation towards the end of the time frequency analysis is because it leads a very sort of easy way to think about Hilbert transform. So let's ask the question, what is the Hilbert transform? And I'm going to use the board for this. Okay, so here's the thing. Suppose I give you a signal, in this case, let's say a sinusoid. Okay, go on, sinusoid like this. And I ask that I want to sorry, just get back here. Okay. So I want to plot function of time the amplitude of the signal, and I want to plot as a time function of time the phase of the signal. So tell me what these two plots are going to look like. What is the amplitude of the sinusoid? So this
1.
is, let's say,
1 and it's constant.
yeah, so here let's say the amplitude here is A. Well, so is the amplitude going back and forth like this, or is it fixed?
It is constant.
It is constant, yeah. So I should get a plot like this where the amplitude is constant. Remember, the signal is going back and forth, but the amplitude is fixed. The amplitude is defined like this. What about the phase? How does the phase change? The phase is this whole thing. Okay, so for a sinusoid, the phase will just change like this. It will just be a linear function whose slope depends on omega, and the phase offset will, whatever, offset you have. So this is omega naught. The derivative of the phase is the frequency, which is again going to be fixed. Okay, so I can say that this signal has this amplitude. Now note that here this is not a function of time, it's just because it's a sinusoid, it's a constant, but the amplitude here is written as a function of time, and so is the phase. So my signal x of t is written in this case as a function of the instantaneous amplitude and the instantaneous phase. So, in this case, you can think of it as an instantaneous amplitude and an instantaneous phase like this. For a sinusoid, it makes sense. AT is just going to be this constant function A, right? And your phase here just going to be here, whose derivative can be thought of as the instantaneous frequency. Instantaneous frequency. Now the question is, can I do this for any signal, even when it's not a sinusoid? Now you might say, hey, this question has no meaning at all. Because, if my signal is doing something like that, what do I mean for it to have an instantaneous amplitude or instantaneous phase? Maybe it doesn't mean anything at all. And in fact, turns out that even though I can compute it using a formula that I'm going to tell you now, it may or may not be very intuitive or useful or meaningful for that matter. Okay, so the goal now, for reasons that will get clear in a bit, is to find a way to write any signal like this as an instantaneous amplitude and an instantaneous phase, and the derivative of this is the instantaneous frequency. So my question is, how would I do that? It may or may not be a useful exercise, but let me ask, how can I do that? So now let's get back to my one signal for which this is at least clear. The meaning is clear because the amplitude is just a constant, and so the phase is a linear function. So if I give you a sinusoid, can you get back two functions, one which is a constant like this, and one which is changing linearly? In other words, can you give me an algorithm or tell me a trick so that when I apply this on this function, instantaneous amplitude becomes a fixed number, a constant, and the phase becomes a linear function like this. Okay, so can I think about this? So here's a sinusoid. Will taking a derivative of this tell you something? No, the derivative is just a cosine. The derivative, you can think of, oh, the signal is changing, so maybe the rate at which it changes tells you about the frequency. The answer is no. The derivative of this function is a cosine, and it neither has a constant, it is varying in the same way as this. How can I get a function out of this which is fixed in time like this, which is my definition of the instantaneous amplitude, and a function like this? And you can think of various transforms, and after a while you will give up, because the transform that I'm going to tell you is a very non-intuitive transform. That is called the Hilbert transform. So let me give you an intuition of that so that it's easier to understand. There's the mathematical formula, which is a bit complicated, but we won't even get into that. I will just give you the intuition. And the intuition is as follows. Suppose I've got a sinusoid to make life easier. Suppose it's a sinusoid multiplied with like so. Okay, and this is in the time domain. So it's peaking at this particular time t. When I want to compute the mean time, which is what I had done, told you earlier. So you do this by integrating with like so. When I do this, the mean time is actually going to be this value here, where it's peaking, because that's where this energy density is peaking. When I do this in the frequency domain, the Fourier transform, now this is frequency domain, and suppose this Gaussian, this thing has a frequency of omega naught, so it's omega naught here. When I want to compute the mean of this distribution, I ought to get this value, correct? But I actually won't get this value. Now, who can tell me why I won't get this value? It's a tricky question, but if you think through this, answer this question. In fact, I'll tell you that the mean frequency is going to be 0. Why? Okay, just to make sure that everybody understands the question, I'm talking about a signal here, which is a Gaussian multiplied by a sinusoid. It's a real signal. And I'm just going to use my previous formula that I had derived, that I had talked about, like this, to estimate the average frequency. And I'm telling you that even though I expect omega naught, the bandwidth here to be whatever this here, my mean frequency, average frequency is going to be 0. And I'm asking you why that is the case. So who can answer this?
I can if nobody else.
Okay, go ahead.
So the Fourier transform of a signal is always symmetric, right, about its x
Very good.
y-axis. So you have that other side
Yes.
also.
Fourier transform of a real signal is always symmetric. So because this is a real signal, it has one lobe at omega naught, but it also has another lobe at minus omega naught. Now, when I square it, the energy density function will now have two lobes. So the mean is always 0. Very good. And this is just a sort of like a technical issue because it's a real signal. It has to be represented by two sinusoids, one sitting here and one sitting there with the phases flipped. But this definition makes my standard usage of the energy density defined this way useless because this thing is always symmetric. So what do you want to do now so that I actually get a meaningful answer whose center is here and the standard deviation is this, rather than the center here and the standard deviation really dependent on how far omega is from 0? The answer is simple. You wipe this out. That's it. If I can transform this so that this lobe gets wiped out, then I'm done. To preserve the energy of the signal, obviously, now I need to make this lobe twice as big as what this is. So if this is A, it ought to be 2A. But now if I can transform my original signal to another signal whose energy is just concentrated on one side, then it's much more convenient for me to use that signal rather than the original signal. So from the energy original signal xt, which has a symmetric Fourier transform, I want to create another signal AT, which I can't draw actually. So this I can draw here. This I cannot draw because this is not a real signal anymore. Any real signal would have this symmetric thing. I want to have another signal whose energy is concentrated only on one side. This signal is called the analytic signal. And this signal is very useful for doing all these kinds of computations. Finding the, the mean frequency and all that, because you're not now, bound by this limitation that the energy has to be split equally in the positive and negative side. And turns out, if you look at this analytic signal is your answer to the first question, which I had. I've got a sinusoid. Its Fourier transform has two components. So if this is amplitude A, sinusoid, its Fourier transform has two components. One sitting at omega naught. So this is A and sine omega naught, let's say T. One side sitting at minus omega naught, right? So it's going, and the amplitude of each is A by 2. Right? So, this is e to the power A by 2, e to the power j omega naught by t minus A by 2 for minus j omega naught t. This is cos omega naught t plus j sine omega naught t. This will also have that cos which will get cancelled, and I have to have a j here like this. So this is the Fourier transform. This is why you have got one amplitude here and one amplitude there of a sinusoid function. But if I look at the analytic signal of this analytic signal, it's just a single delta function of amplitude A and at omega naught. So the analytic signal is just A e to the power j omega naught t. So it has a linear phase and a constant amplitude. So if I compute the analytic signal and ask what its instantaneous phase is, it's this, it's a constant. And what its instantaneous the instantaneous phase is, that's this. Its instantaneous amplitude is just A. So the trick is that once I give to compute its analytic signal AT, and this signal is a complex function which can be written as a complex amplitude e to the power complex phase, both as a function of time. And then the instantaneous amplitude of xt is given by this AT, and the instantaneous phase is given by phi t. And this could be done for any signal, not just a sinusoid. For a sinusoid, it will make AT a constant and phi t linear. And what is the analytic signal? The analytic signal is simply a signal whose Fourier transform, unlike the original signal, is just concentrated on one half. That's it. Okay, so if I've got a signal which has a Fourier transform that looks like this, some arbitrary Fourier transform, consider this as a linear signal. You transform this to another signal which is twice on one side and 0 on the other side. This is the analytic signal. Once you do that, this is not a real signal. It's a complex signal, so it will have a complex amplitude and a complex, it can be written like this. And then the instantaneous amplitude is defined as the amplitude of the analytic signal, and the instantaneous phase is defined like this. This is the definition. And the reason why this works is because of what I told you here, that it works perfectly for a sinusoid. You put this back here essentially, and you're getting this as A E j omega t. So you get the constant amplitude and the linear phase. Okay, let me just show this to you guys so that is a fair bit to understand. So let me just quickly show this to you. So here I have got Fs of 1000, t is 1 second. I'm generating a sinusoid xt. So plot x. So it's a sinusoid, 100 hertz, right? The FFT is going to be a delta function at 100. So, so one peak at 100, one at 900, because it's symmetric. Now, the analytic function is obtained by this formula. And I'll tell you why it's called Hilbert. So now if I try to plot Z, this is complex, so this is how it's going to look like. If I say plot real or first, let's plot the abs FFT of Z. And notice now that it has wiped out this 900 one. 900 and minus 100 are equivalent. And this, it's the full value. The X was, hold on. Yeah, so this was half the size. Stem here. This was half the size, but 2 lobes. I have wiped this out and I made a single lobe. But now, because of this, my Z is now a complex number. So if I try to plot Z, this is complex, so it looks nothing. If I plot real part of Z, it's the same as that sinusoid. Imaginary part of Z is going to be slightly shifted version of this. Okay, I guess it's harder to see. Let me just change the frequency to 20. It'll be easier for you guys to see this. Plot real Z. Okay, so this is the same as, hold on, as your original sinusoid. They're the same. And the imaginary part is slightly shifted. Like that. Oops. However, so you can see that the real part and imaginary part are, slightly shifted version. If I ask what is the amplitude of Z, plot the abs of Z. What do you think it's going to be? It's a flat line. Okay, it's at 1. This is 1 point. So y lim 0 to 2. So I have got what I wanted. I've got a signal Z, which is the analytic signal of X, and the absolute value, the amplitude, the instantaneous amplitude is 1. So this function tells you that the amplitude is everywhere 1. And what's the phase of Z? It's this linear function. Okay, so it's changing between minus pi and pi. If I unwrap it, it will become completely unwrapped. It's a linear function. So the derivative of this diff oh so I'll just plot this. Derivative is now is going to give you the instantaneous frequency, so it is also a fixed number. .02, which is the normalized frequency here corresponding to 20. Okay, so I have got my answers. I have created a signal Z such that its absolute value is a constant, which is what I know for a sinusoid, and its phase is changing linearly. Okay, so
Excuse me.
this is, yeah.
What does unwrap do actually?
Oh, unwrap is just a function that if I don't unwrap it, it will give you values between minus pi and pi. And if you unwrap it, then it will just keep increasing on top of pi. So it doesn't bring it back between minus pi and pi. It doesn't matter, right? Because its phase of pi plus x is the same as minus pi plus x, because it's circular about 2 pi.
Okay.
Yeah, I just wanted to show that it's actually changing linearly. This is just chopping it up and keeping it between minus pi and pi, because phase it's circular, shifted. If you add 2 pi to a phase, you don't do anything. That's all. Okay. So yeah, I'll encourage you to just do this for other functions also, to make an understand, to try to understand what is going on here. So for example, let's say I take this signal and this is this signal is 1 everywhere in the frequency domain. It's a delta function. A signal in time domain, plot x, it's 1 and then 0 everywhere. So it's 1 and then 0. This is in the time domain. In frequency domain, it has become a delta function like this. Now I take the Hilbert transform and I plot the absolute value of Z. So now notice how it is changing here. Absolute value of FFT of Z. Let's first look at that. So this will be 2 here between 0 and 500, and then it's getting wiped out. And if I look at the angle of this, again, you will see that it's 0 everywhere between 0 and 500. Here it doesn't matter because the amplitude is 0. So the Hilbert transform has actually changed it so that the energy is only concentrated between half the frequency range, 0 to 500, and otherwise it's 0. And then the instantaneous amplitude of a delta function is actually this, and its instantaneous phase is going to be like this. Okay, the phase is all over the place. Oops. 0 and pi by 2, and then it changes. So a simple function like this can have sort of very complex meaning in terms of instantaneous amplitude and instantaneous phase. In this case, because it is just a delta function, its meaning in terms of instantaneous amplitude and instantaneous phase is unclear. That is what I was trying to say, that what this means is actually quite unclear if it's not a sinusoid. But we will see that we can make it clearer and use it for understanding a signal in time frequency domain by first pre-filtering the signal and then looking at it. Let's do one more. It's now a sinusoid, and the first value is 1. So it's a sinusoid and a delta function. So I've got a delta function, but these values are also non-zero now, some small value. Let me take the Hilbert transform and plot the absolute value of the FFT of Z. So again, you can see that it has become 1000 here, and otherwise it's 0. Let me plot the absolute value of Z. So here it is the absolute value of Z, and you can see that it's telling you that the more or less the instantaneous amplitude is close to 1. But because I put a delta function, it has changed this initial part a little bit. Okay. So let me just finish off by telling you why this is called a Hilbert transform. I told you that the name of the signal is analytic signal. But to reconstruct the analytic signal, here's the process. So I've got a signal xt. I want to generate, okay, so from this I want to generate a signal at such that if xt is symmetric here in the frequency domain, at is concentrated on one side. So how do I do this? Now here's an idea. I take xt and its frequency in the frequency domain, the amplitude is symmetric. This is the amplitude, and the phase is anti-symmetric. So whatever the phase is here, it's the opposite here. Now suppose I do something to the signal. So I h of xt. So I've done something to the signal which shifts the phase of only one side by 180 degrees. So it will actually keep the phase here as it is, but it will actually flip the phase on the other side by 180 degrees. So that when I add the original signal and some transformed version of this lobe essentially gets wiped out. Because, so if this is a vector in one direction, I'm just creating the opposite vector, but only in the negative frequencies. Oh, actually, I didn't draw this properly. This is not a reflection here. It will keep the phase on one side unchanged. It will actually shift this whole thing by 180 degrees. Okay, so that when I add the original signal with this transformed signal, I wipe out this side completely, and I only get twice on this side. Turns out this transformation is J times the Hilbert transform. Hilbert transform is a transform which yanks the phase by minus 90 degrees on the positive side and plus 90 degrees on the negative side. This formula is a little bit complicated, so don't worry about it. It's basically a transform which changes the phase by minus 90 degrees on the positive omega axis and plus 90 degrees by in the negative omega axis. When I multiply it by J, which is a positive 90 everywhere, essentially it becomes 0 here and 180 on this side. So essentially I'm flipping the vectors by 180 degrees everywhere on the negative axis, and by I'm not doing anything on the positive axis. So the analytic signal AT is nothing but X, the original signal, plus J times the Hilbert transform of XT. And it is so popular that the analytic signal is sometimes called the Hilbert transform of X. But this is why the Hilbert comes in. Okay, so it's a single command in MATLAB, Hilbert of X. But what it's doing is actually doing this thing here. It's actually xt plus j times Hilbert transform of xt. Which is why when I computed z this way, the real part of x was exactly the original x, and the imaginary part was a shifted version of this. This is the Hilbert transform that we got in the imaginary part. Okay, so that's that. This is how Hilbert transform works. And the analytic signal is awesome because you can now estimate a instantaneous amplitude and instantaneous phase for any signal. Could be a random signal for, X could be completely random signal. X is rand 1 2000. Plot of X. It's completely random, but I can still compute an instantaneous amplitude and instantaneous phase just by doing the Hilbert transform of this. Okay, so now I create an analytic signal Z. Now plot abs FFT X. This is this random stuff here. Plot abs FFT of Z. It gets double on the positive side, becomes 0 here. See that? And now that I have got Z, the instantaneous amplitude is just absolute value of Z. And it looks pretty much like the original signal. And the angle is this. The phase is this. And it's also random. So for any signal, I have now, I'm able to compute an instantaneous amplitude and instantaneous phase. It may or may not be useful, but this is the procedure. Okay. In the next class, we'll useful and see how we can actually use the Hilbert transform to compute one transform, which in some cases gives a very nice representation of the signal in time and frequency domains. Okay, so sorry, I spilled over a little bit over time, so I'll finish the class now. If there are any questions, please go ahead. Otherwise, the class is over.